Good afternoon, everyone. So today I will talk about microcantilever-based hydrogen sensor. So it's basically a dynamic sensor. So I'll discuss about its fabrication and response dynamics. And further, I will talk about how we are going to sense with this dynamic sensor. Even the squeezable damping is present in the system. Since squeezable damping basically deteriorates the performance of the sensor, but still how we can utilize the sensor in order to sense the hydrogen. So if we see this dynamic sensor, they can find application in various domains like for single molecule protein detection, single spin detection. People have made pressure sensor with this micro and nano electromechanical sensor. Researchers have recently shown that shown the mass spectrometry with this resonator-based sensor at atmospheric pressure. This sensor can find application in accelerometer, gyroscope, and recently, researchers has reached to a limit that they can be able to measure the mass of a proton with this kind of sensors. So they are basically very high sensitive. Turning our attention to gas sensor, if you see the recent trend, in the gas sensor, the growth is very high and it's reached to about $1 billion because of its application in various domains like in aerospace, medical health, environmental monitoring, industrial application, and in the recent era smart system, it can find application in smart wear, smart homes, food safety. So let's discuss how these sensors work, this resonator-based dynamic sensor. Consider any resonator, basically any suspending structure, it will have its resonance frequency. It's depend upon the stiffness and the mass of the resonator. Now, if something gets deposited on this resonator, its frequency shifts. And that frequency will either decrease or increase based on the change in stiffness of the resonator or the mass of the resonator. Again, as I have mentioned that these sensors are very sensitive that it can able to measure the mass of the proton by choosing the proper geometry. This sensor will have very high responsivity and very high sensitivity. Also, these sensors are array compatible and we can make it more portable by adding all the electronic circuitry around it. So I will discuss about the fabrication of my dynamic cantilever devices. For that, I have used SiO2 wafer. So SI is basically a highly doped vapor here I have used. Then after I've used silicon nitride as the structural layer for the cantilever, and I deposited metal electrode basically to act as a top electrode for electrostatic actuation. And then I had defined the cantilever and weightage and critical point right to suspend the cantilever. So after suspending the cantilever, I put a manual mask and deposit palladium on certain portion of the cantilever. So palladium thickness is about 10 nanometer and it has the great affinity for hydrogen. So this is the final fabricated devices, and you can see on the tip there's the palladium deposited in certain section of the device. Now, in order to measure the response of this cantilever, basically I have used electrostatic actuation and optical detection. So this optical detection is with LDV, laser Doppler vibrometer. And I have used external lock-in amplifier in order to measure the response of the device in real time. This lock-in has an inbuilt PLL system. So in order to track the resonance frequency in real time, I've used this Zurich instrument lock-in amplifier. So as you can see, this setup, the device is below this LDV, and once the device actuates with the signal output, basically with the electrostatic actuation, this motion is transduced with this LDV setup. And the signal is fed into this lock-in amplifier. And see, have performed both the open loop and closed loop measurements. So in open loop, see, this is the amplitude versus frequency response of the device at different actuation forces. In electrostatic actuation, the forces is proportional to the gradient of capacitance times the actuation voltages that we are applying. So as you can see, I'm keeping the DC voltage constant here, and by varying the AC voltage, initially the device is in linear regime, but after certain voltage, you can observe a sudden jump in the frequency here. And that's basically says the maximum limit of operation of the device in linear regime. So based on this, you can see this inset. With the increase in actuation voltages, the amplitude increases linearly, but after certain voltages or basically the forces, the amplitude starts saturate. So that's basically defines the critical amplitude of the device, after which we observe this sudden jump in the frequency, or basically once we do open and closed loop measurement, we get a hysteresis in the loop. So in order to operate our devices at the onset of nonlinearity, basically we use the general convention of 1 dB compression points, and that's basically limits the maximum dynamic range of the device. So this dynamic range is basically the logarithmic of the maximum signal that we measure to the minimum signal that we measure through this device. And that limits the maximum linear range of the operation of the device. So with that data, we basically get the maximum operation point in linear region that's given as the VGDC of 1 volt and VGDC of 120 millivolt. And the dynamic range of the device is about 58 dB. Now, in order to perform the gas sensing and track the region, basically do the measurements in real time, we basically mounted our device inside this vacuum chamber that's kept below this LDB setup. And this gas cylinders, this is connected to this chamber with this ball valve arrangement. And here basically I perform the static mixing of the gases, basically mixing of hydrogen with nitrogen, and the response is being tracked with this lock-in amplifier inbuilt PLL circuit. So this is the data, experimental data. Once I was flowing a pulse of only nitrogen. In that case, we observe a positive frequency shift. But when we mix the gases with hydrogen, we observe a small positive shift, and there is a negative frequency shift. And if we further increase the concentration of hydrogen, we can see the positive shift has further decreased and negative shift has increased. So why we are observing the positive shift? Because see, whenever the gas adsorbs on the resonator, its effective mass changes and basically the frequency shift should decrease. But here with 0% of hydrogen and only the nitrogen, we observe positive frequency shift. So that's happening because of the squeeze field damping. So what happens whenever we flow the gases reaches to the cantilever and between the cantilever and substrate. So this device is, I forgot to mention, it's a surface micro machine device. So whenever the gases reach between the substrate and the cantilever, it gets squeezed. And based on this cutoff frequency, if our device operation is below this cutoff frequency, then this squeeze field damping basically deterred the performance of the resonator and damped the oscillation. But if we operate the devices above that cutoff frequency, then it will act in elastic domain, and it's only change the stiffness of the resonator instead of the damping thing. Again, this squeeze field number defines how well the gases is being trapped within this cantilever and the substrate. Higher is the value, higher will be the trapping. So based on this, the stiffness change due to the gas getting trapped within this resonator will be given by this ambient pressure in the chamber times the area of the resonator and the gap between the resonator and the substrate. So based on this, we calculate this frequency shift. Now let's understand why we are getting this kind of data. Like once we flow this pulse, pure nitrogen pulse, we observe this positive frequency shift. And that was happening because of the squeeze field damping, because there wasn't any affinity for palladium with nitrogen. But once I mix this, so as you can see in the left and the right side, there's an illustration which shows the pulse. So initially when I flow the pulse, the pressure in the chamber rises from -4 millibar to -3 millibar. And then again, since the pump is continuously on, it's again pump out the gases. So in that case, the frequency is initially increasing. That's because of the squeeze field damping. But once we mix it with 0.5% of hydrogen, we observe that the positive frequency shift peak has decreased and we observe a negative frequency shift. So here what's happening is that initially, once we flow the pulse, we observe this positive shift, but at the time, the adsorption is also happening on the peak. And this absorption is given by this rate equation. So during that time, after certain time, it's basically balanced this squeeze film effect. And after this, we observe this negative thing. And again, the desorption happens. Once we further increase the concentration, so the rate will again be higher at 1% concentration. As you can see in the rate equation, it depends upon the partial pressure of the gases. And once we increase the concentration to two times, obviously the rate will be 2 times higher. So in that case, it's quickly balanced the squeeze field damping effect, and then we observe a negative frequency shift. So as you can see, the T2 should be half times the T1, and that's what we observed experimentally. And in order to study this, I mean, if there is squeeze field damping present, so in order to study the response, we basically, the overall frequency shift will be given by this positive frequency shift times this negative frequency shift. So if I have got the theoretical positive frequency shift that I have observed is about 60 Hz, but experimentally that we have observed based on The theoretical that I have calculated is 60 Hz, but experimentally I have observed about 47 Hz. Now, if we see this table, you can see that the concentration of hydrogen at 0% concentration, we observed this 47 Hz frequency shift, but there wasn't any negative shift because there wasn't any absorption happening. And time scale when absorption began, basically there wasn't any absorption happening at 0%, but at 0.5%, the positive frequency shift decreases, but the negative shift increases. And the time point where the absorption begins is 0.8 seconds. At 1%, again, further the positive shift decreases and the negative frequency shift has become 2 times, and the T2 time that I was discussing is about half of the T1 times. So that's basically explain the behavior. And now further, this shows the repeatability of the sensor with the hydrogen, 1% hydrogen gas. Further, we have performed the frequency stability measurement to set the minimum limit of detection of the devices. So for this, we basically perform this frequency stability measurement that's basically done by Ln deviation measurement. So this is the data that shows the Ln deviation measurement at different integration time. And based on this, we calculated the minimum frequency stability is about, the best frequency stability is about 8e-7 at 1 second integration time. And the frequency resolution we observed is about 0.31 Hertz. So based on this, we observed a gas resolution of 0.0031%. That's much better than the previously reported data. So in conclusion, we have shown hydrogen sensing with this microcantilever-based sensor, and even if there is a squeezeful damping present, how we can analyze this data. And we have shown this highly sensitive H2 sensor with much better sensitivity than the previously reported resonator-based sensitivity. Thank you for the attention.